Hello and welcome to Enough with the Science. I'm Joe.
And I am Senan, and this week we're delving into the mysteries below the ocean floor to discover all about the Jacuzzi of Despair.
That's just basic a summary of my entire life.
The jacuzzi part or the despair part?
Well, there's a lot of despair and there's a lot of water. So
does your desperation bubble up mysteriously?
yes, only when you ask me questions like that. I'm usually grand before that.
Yeah.
But yes.
So we're going to be talking about some of the stuff that's on the floor of the sea. It's not what everybody possibly thinks. It's just a featureless desert down there, but there's a lot more to it than that. There's volcanoes, there's lakes, there's nodules, and of course, my personal favorite, the zombie bacteria.
And this is all in the pitch dark.
Oh, sure, yeah. I mean, once you go down deeper than, like, I guess, 80, 90 meters, the light doesn't penetrate any deeper than that. But the ocean is a hell of a lot deeper than that. So, yeah.
And there's a point where you, like, if you drop a person or something into the ocean, there's a point where they will just naturally sink and continue to sink indefinitely.
So I guess what you're talking about there is pressure. If you take a lungful of air, and you hold your breath and you jump into the sea, initially your head might go under the water, but if you just keep holding your breath, you'll pop back up again because your chest is full of air and that's acting like a float, keeping you up. But if somebody was to actually then, if you keep holding your breath, but somebody was to actually then drag you down into the depths, we'll say it's like the concrete boots the mafia use. What's happening is the pressure is increasing as you go down, down, down. And in fact, a lot of the stuff we're going to talk about today is related to pressure and increasing pressure, because the deeper you go into the sea, the more the pressure increases, and it increases dramatically. So if you're standing on the beach, the air pressure that's pressing in on all sides of your body is roughly 1 kilogram per square centimeter. So that's like, if you look at the nail on your pinky, that's like, for most people, roughly 1 square centimeter. So there's about a kilogram pushing in on that and every other square centimeter in your body. If you go into the ocean, and that, by the way, is the weight of the air above you.
So if I wanted to lose weight, I just have to climb a mountain.
Well, yeah. You might lose pressure. I'm not sure about losing weight.
Damn it.
You would actually lose a slight little bit of weight because you'd be that little bit further away from the centre of gravity of the Earth. But
I was right.
It'd be hard to measure it.
It doesn't happen very often.
But anyway, so as I said, it's roughly 1 kilogram per square centimetre while you're standing on the beach. You hop into the sea, put on your scuba gear, and you go down 10 metres. And now you've doubled it. Now it's 2 kilograms on every square centimetre. And you go down another 10 metres and it's another kilogram. So that's 3 kilograms now, and so on. So for every 10 metres further down you go into the ocean, the pressure increases by roughly 1 kilogram per square centimetre. So when you go to the really deep ocean, you're talking about massive amounts of pressure, and that has all kinds of interesting effects.
Okay, such as?
Such as, let's say, a ship sinks. And there's a trapped airspace, like some kind of a tank or something in the ship that's full of air. And the ship sinks towards the seabed. Eventually it reaches a point where the pressure that's on the outside of that tank is greater than the strength of the metal the tank is made from, and it just crushes it because the air in the tank is compressible. So it's like any gas, it can be squashed by pressure. So the air in the tank is not offering any resistance, really, or very little resistance to the pressure of the seawater. So all that's stopping the tank from getting crushed is the actual strength of the metal. So eventually the pressure of the seawater as the ship is sinking towards the bottom just exceeds the strength of the metal and squashes it. So that's an example of the kind of...
So once like a ship starts sinking towards the bottom, it gets to a certain depth and it just like squishes like a can.
Well, only the enclosed airspace is in the ship.
Okay.
So probably most of the ship, the water can find its way into the inside while it's sinking. Mm-hmm. Right. That then doesn't crush the ship. So the metal, the solid metal of the ship, as long as there isn't enclosed air within it, doesn't really get crushed by the water.
So it still resembles a ship then on the
seabed. It does. I mean, when it crashes into the seabed, it might actually get buckled or something by the force of the crash. But other than that, yes, it typically resembles a ship when it gets down to the bottom.
And so what sort of world is it going to experience now when it sinks gently to the bottom of...
Well, of course, there's the zombie bacteria. We can't let
We're just not going to give it up with the zombie bacteria.
We cannot finish today's discussion without mentioning the zombie bacteria. So some of these guys could have been alive for 100 million years. That's the same organism. We're not talking about his parents or his grandparents. Some of these...
It's not a species, so this is one. This is a single individual...
well, I mean, yeah, it's a species, but some members of that species may be alive. And the reason for that is, so these guys are...
lazy. They're lazy. They don't do anything.
They're underneath the sediment in the really deepest parts of the ocean. So down there's practically no oxygen dissolved in the water. There's almost no nutrients for them to exist on. It's extreme. There's extreme pressure, which just makes it difficult for any living creature to survive. And then it's very cold as well. So that's take all those things together. It's a real extreme environment. And those creatures have evolved to have an ultra slow metabolism. So their chemical processes in their body work far, far slower than ours, which allows them to exist without using much energy, and individuals then live for a long time.
Could this be like some used as an excuse for not being particularly productive in work? That you have just
there's too much pressure.
There's too much pressure.
Sorry, I can't do my work. There's just too much pressure, and it's awfully cold in here.
And so they're zombies because they're almost dead, or they're
because they're like the living dead. Yeah. And it's interesting for scientists to study them because it's theorized that if we find alien life on other planets, it may be in the form of bacteria of some kind. And say the moons of Jupiter or the moons of Saturn, some of them are covered in ice, extremely cold, but probably have liquid oceans underneath the ice. And it's possible we may find bacteria like this, in those places. So it's useful to study these
And how did these guys decide where to end up? It's just luck?
Well, life tends to find a niche. Like anywhere that life can possibly exist, it generally will exist eventually. Something will evolve to fill that gap. So, the bacteria, they probably started out, or their ancestors probably started out their lives as fairly ordinary bacteria living on the surface of the earth, somehow found their way down to the seabed, maybe in the body of a dead fish or something, who knows.
Okay.
So yes, that's the zombie bacteria. Now, another cool and slightly weird thing is the brine pools, are also known as the upside down lakes.
Yeah, I like this idea. An upside down lake.
So it's weird to think that like down in the seabed there can be a lake that's not the sea. It's like a separate body of water. Even it's like a sea within a sea, if you like. Yeah. And what we're talking about here is some pockets of water that have become gradually more and more and more salty, and that makes them denser. So the really, really salty water is much denser than ordinary seawater, and it tends to sink underneath the ordinary seawater. It sits on the seabed and it finds depressions in the seabed. So any little bowls or hollows in the seabed, it just naturally flows into them because it's denser, heavier than the normal seawater, and then it just sits there, and you get these almost stagnant, not quite stagnant, but these ponds that are sitting on the seafloor that don't change very much for thousands of years.
And these were discovered just by virtue of how salty they were, or...
Yeah, I think one aspect of them is very, very few sea creatures can survive in such salty environments. So, it's like the Hotel California. If you're a fish, you can enter, but you can never leave because the salt in there will kill you. So if you happen to swim into it, that's it. You're a goner in a few minutes because your body just can't cope with that salt. And that's where we spoke earlier about the Jacuzzi of Despair. That's one particular notable brine pool in the Gulf of Mexico that is particularly salty, and practically everything that wanders in there dies.
And what kind of size are we talking about? Are we talking about Puddles? Are we talking about?
Oh no, I mean, like potentially we could be talking about something the size of a lake that's on land.
Right.
You know, I mean, it's if the depression is big enough, the hollow in the seabed is big enough, then eventually more and more of that stuff is going to collect in there.
And so that's connected to the whole despair thing, the depression.
But yeah, it is. But of course, as I mentioned earlier, life can find a way, and there are extremophile bacteria living in there.
You just love that word. I think
and I suppose our zombies from earlier are another example. Extremophile just means bacteria that are able to live in extreme environments that most creatures can't live in. So these guys have evolved super tough cell walls, so the salt can't destroy the walls of their cells, and the chemical processes have adapted to high concentrations of salt. And they're able to eke out a living there where nothing else can. Nothing else other than tube worms. And the tube worms. Tube worms. Tube worms. There are lots of species of tube worms, and they're called that because they literally construct like a tube, like a straw sticking up out of the seabed, and they live inside in that tube. They poke their heads out to get food or whatever, but that's like their refuge. They build their own house.
So they're kind of like the apex predator of the Jacuzzi of Despair.
There's not a lot of competition really.
Yeah.
So they have a kind of a symbiotic relationship with the bacteria I mentioned earlier. So the bacteria have figured out how to harvest energy from the chemical processes in the salty water, and the tube worms are piggybacking on that and borrowing energy from the bacteria.
Not really selling this as a holiday destination, though.
Well, you just never know. I mean, some people want to chill out, and by God, you could certainly chill out on the ocean floor.
So again, because I'm trying to picture these things, but of course, this is all in pitch black, in the minus gazillions of degrees, cold, and with like pressure.
Yeah, ridiculous amounts of pressure. Yeah. It's like an unimaginable environment. In fact, if you try and compare it with, say, being an astronaut in space wearing a spacesuit, that environment where there's no air, that's actually a far more benign environment, because the astronaut's suit only has to hold in 1 atmosphere of air. That's roughly 1 kilo per square centimetre. Whereas if you have an aquanaut, we'll call him an underwater astronaut who goes down to these extreme depths, his suit might have to withstand hundreds of atmospheres, hundreds of kilograms per cubic centimetre. So it's actually quite a hostile environment.
Kind of a Tony Stark type Iron Man suit.
That's it. But while we're on the subject of weird things on the seabed, the explosive mud volcanoes are the next one on the list.
And I don't know where this podcast just veers into your imagination, the wonderful imagination of
I didn't imagine them, they exist.
Exploding mud volcanoes.
So, I mean, we should point out now, this is not the only type of volcano on the seabed. There are like proper lava volcanoes like we're used to here on the surface of the earth down there also. And then that's a complete other story. Those are some really interesting chemistry going on around them. Anyway, the mud volcanoes, though, are a different animal altogether. They're nothing to do with lava or magma or anything like that. What happens is you've got these layers, really thick layers of silt and sediment that have loads of dead organic material in them. So that is, dead fish, dead seaweed, fish poo, and possibly. For those who don't know, who don't understand that reference, it was a famous horse that was kidnapped and never turned up.
Yep.
Anyway. These organic materials that are in the silt on the seabed are gradually decomposing, and methane gas is released as that organic material is decomposing. And sometimes if the silt or the sediment is really dense, that methane gas will build up in a pocket, an enormous pocket underneath tens or hundreds of meters of silt. So you've got this like reservoir of methane gas that's gradually building up. And then sometimes the pressure in it increases because it's confined in a tight space. And eventually the pressure of the methane overcomes the strength of the pile of mud that's on top of it, and it literally explodes. So you get this huge outpouring of trapped methane gas, like a volcano that splatters mud up into the water column,
But it's not on fire. It's just gas thrown mud.
So although methane is flammable,
There's nothing to...
It would be very difficult. For starters, there's not much oxygen down there, so the methane would need oxygen to combust. But even, obviously, the presence of water would make it very difficult for it to actually go on fire. But it has some very interesting and weird potential ramifications. One is that it could sink ships that are above it. So the reason for that, and it's not proven that this has happened, but it is...
Bermuda Triangle. This is Bermuda Triangle territory.
This could well be the cause of the Bermuda Triangle. Essentially what's happening is that you get this massive sudden release of methane, way down, several kilometres down below the surface of the sea, on the seabed. And as it bubbles up towards the surface, the bubbles get smaller and spread out more and more and more. So you get like this fizz in the water of methane bubbles. And that water, effectively, its density is now being lowered by all this gas that's mixed in with it. And the Archimedes principle that allows boats to float on the surface of the sea relies on the water having a certain amount of density. So the less dense the water is, the harder it is to get something to float on top of it. Right. So potentially, if that fizz of methane bubbles comes up around a ship, it could locally reduce the density in that area and allow the ship to actually sink, because the density of the water is temporarily reduced enough to not allow the ship to float. So it's pretty scary stuff. Now, no actual recorded case of it's happening, but then again, would anybody survive?
Well, all those ships that went missing. How did he explain the planes, though? Would it affect the planes in the Bermuda Triangle?
I don't think so. I don't think it would, unless something ignited this huge cloud of methane and just burnt the plane out of the sky. But I suppose anything's possible.
Unfortunately, we might return to this in our investigation series.
I want to go back to something you mentioned a minute ago, and that you said could these methane volcanoes go on fire? Not themselves, but there's a very interesting thing happens with methane at great depth and pressure and low temperature. It combines with the seawater to form something that we call fire ice. So it's a peculiar mashup of frozen seawater.
Now we're into Game of Thrones territory, fire ice stuff.
So it's really one of those really peculiar substances that only forms down at the seabed under the right temperature and pressure. It essentially locks up the methane in this icy, slushy substance, and if you retrieve some of that and bring it back to the surface, it's quite unstable. It needs that pressure and temperature to maintain its structure. Mm-hmm. So when you bring it back up to the surface, the pressure reduces, the water is warmer. When it comes into contact with the oxygen in the air, when you bring it out of the sea, it can suddenly burst into flames. Right. So you can get this spontaneous combustion just by virtue of the fact that you have brought it into contact with oxygen at lower pressure than where it would normally live.
This must have been a kind of unpleasant surprise for the first people who brought it up.
Yeah, absolutely. And I mean, it's something we'll touch on later. There's people trying to figure out how to mine this stuff, because methane is a fuel. You can, in fact, rockets use it. And if this stuff is just lying around in the seabed, if we could figure out a way of bringing it to the surface without it getting unstable and just evaporating and burning, we might be able to harvest that fuel and make good use of it. Mind you, we probably have enough hydrocarbons already being burnt in the planet without more.
But because of the pressure, though, at where it is on the seabed, obviously it's squished into so when you bring it up, it will be expanding the whole time you're bringing it to the surface.
I'm not sure. Does it? I know there has been cases of where it has been brought to the surface and it spontaneously bursts into flames. So whether some of it kind of evaporates or dissolves away while you're bringing it to the surface, I'm not sure, to be honest with you. But I guess it sounds based on those occurrences that have happened. It looks like it's possible to get it to the surface in one piece. Mining it may well prove to be possible in the future, but it might not be a good idea from a global warming perspective.
When has that ever stopped us?
Yeah, indeed. So the next, while we're on the subject of mining,
here we go.
We're going to talk about something with the cool name of manganese nodules.
That sounds something like you have to go and see a specialist for.
So these are effectively sea potatoes. So
right.
They're little lumps lying around in certain parts of the seabed, about the size of a potato and composed of mostly manganese metal. they have formed incredibly slowly. And again, it's down to the temperature and the pressure at those depths to allow them form. But there is minute trace amounts of manganese dissolved in seawater. So, the seawater at some point in its life cycle has been in contact with rocks which had manganese in them. Some of that manganese has dissolved out of the rocks, or maybe volcanoes, underwater volcanoes have carried up manganese that has dissolved into the seawater. So anyway, somewhere along the way, the seawater picked up this tiny, tiny, tiny amount of manganese. And the conditions are right at the seabed in certain places for that manganese to gradually harden into these little nodules, but it's an incredibly slow process. So it's estimated that these nodules get bigger by 1 centimeter every million years. So, come back in a million years, you might just be able to.
Sport watching this.
Yeah, if you measured the width of one of these little sea potatoes, it might be a slight little bit bigger than it was a million years ago. But there are, in certain places, tons and tons and tons of them just lying on the seabed with this valuable precious metal waiting for us to pick them up. So there are companies working on mining that stuff, but of course, like anything else that involves mining the seabed, there's huge environmental risks because if you have to tear up huge chunks of the seabed to get a decent quantity of this thing,
you could just put a magnet on a string.
Yeah, I don't know if it's manganese magnetic. I don't know. I know manganese. Yeah. One would think it might be magnetic. One would think it
would be attracted to magnets.
That's our homework for our listeners this week is to Google whether manganese
is manganese magnetic.
Magnetic or not.
We come up with more questions than answers. But what's it used for? What do we use manganese for? Kind of make a good curry?
That is the second part of our listeners' homework this week.
If they're going to go through all this trouble to get the manganese up and then realise, actually, we have no use for this.
It's a convenient paperweight. But you mentioned earlier on ships sinking.
Oh yeah,
and
that was the methane. Methane explosions.
Yeah.
And loose lips apparently.
Loose lips.
Yeah, sink ships apparently.
Allegedly, and particularly after you've had plenty of pints of beer, trying to say that is definitely going to sink whatever ship you're on. Anyway, we should probably talk about the deepest known shipwreck.
Okay.
And that's a World War II vessel from the United States called the USS Samuel B. Roberts. I have no idea who Samuel is before you ask me.
Yeah. I was going to actually. Everybody knows who Samuel B. Roberts is.
Anyway, this boat is nearly 7 kilometers down. So that is significantly deeper than the famous Titanic wreck, for example. Pressure massive down there. So its pressure is nearly 700 times the pressure of what we have here on the surface. So if you imagine every square centimetre of that boat is being subjected to about 700 kilograms of weight from the pressure of the water. Needless to say, any enclosed airspaces in that boat have long since collapsed. But it is there are almost no submarines that we have developed capable of going down to those depths because of the pressure. Because remember, if humans want to go down in a submarine, there's got to be an enclosed airspace. That's the air those humans are going to breathe. So the structure of the submarine has got to be strong enough. And of course, there's that famous case from a couple of years ago of that private submarine that went down to the Titanic and imploded under the pressure. It was generally any of these really deep vessels are only going to be explored using robots that the robots don't require an enclosed airspace.
Okay, so it's like a drone essentially.
Like we do. Yeah, an underwater drone, but it's still technically challenging to build a robot that will function correctly at that depth and temperature and pressure, of course. That's it. It is a useful. It allows deep shipwrecks like that allow scientists to discover how metals and other materials degrade in a very extreme environment. So you learn new things about metals and how they degrade.
And would they normally, like with the drones, would they send out like a submarine a certain depth and then fire off the drones, or they just send the drones out from the ships?
Most of them, the drones are tethered from a ship, so there's like a long cable going down to the drone. Unlike obviously flying drones use radio waves typically to be controlled, but it's not really feasible in the sea because radio waves don't travel very well underwater. So usually there's a cable involved. So you can imagine you've got your 7 kilometer long cable. Imagine the storage.
Driving that.
Imagine the storage space you would need on the ship for 7 kilometers of cable. So it's
and just with that particular ship, where is 7 kilometers deep? Where is it?
Pacific? I'm guessing it's probably in the Pacific, because in World War II, most of the US activity was in the Pacific, but I'm not certain. I honestly could be wrong about that.
There's a full quiz for listeners this week.
Yeah.
A selection of questions.
We'll be expecting all of those things to be answered by our listeners in the next week or so. Lost continents.
Very good. Yeah, here's the intro. Atlantis. I knew it. I knew we were going to get to Atlantis.
Lost continents. So it's a thing. Atlantis, probably a myth, but lost continents are really a thing. There's a famous one, the most famous one, called Zealandia in the Pacific. It was huge. It was half the size of Australia. And it essentially something called plate tectonics did it in. What's plate tectonics? As a lot of people probably know the answer to this, but I guess we should probably talk about briefly what it is.
It's what you do before, when you're organising your wedding and you're trying to decide what type of glassware and cutlery and plates you want.
Yeah.
It's the science of that. There must be a science of that. People spend months choosing stuff.
So it's the Earth really is like an egg. There's this very thin shell of solid ground that we live on, called the land, and underneath it there's this massive amount of gooey magma that most of the planet is composed from this liquid, and the shell is just floating around on top of the liquid. So the land we live on is a thin crust that's just floating around on top of this molten lava, and it's actually not unlike an eggshell, a chicken's egg or whatever. It's not like one complete unbroken shell. It's like several different slabs that are floating around, and we call those plates. We call those the geological or tectonic plates. And there are currents in the magma, in the lava, in the center of the Earth, because of differences in temperature. Some places are hotter than others. There are convection currents that slowly move the plates around. So we're floating on top of this goo, and it is moving slowly and pushing us along with it. So in the case of poor old Zealandia, the lost continent, what happened was the plate that it's on got pulled apart by 2 different currents that were essentially pulling at different sides of the plate in different directions. So it got stretched, and it got thinner and thinner and thinner, and eventually it was so thin that it wasn't high enough to poke above the waves, and it sank into the sea.
Right.
So because the land literally got stretched.
Now this didn't happen in 15 minutes. Obviously, this was
no.
Yeah.
I'm sure the locals probably had time to evacuate.
Were there locals even when this was occurring?
You have me there. I mean, we're talking about a long time ago, so the locals probably didn't look like humans.
Right.
They probably had horns and scales and
the dinosaurs.
Yeah, quite possibly. Yeah. And there's actually another one as well. So Zealandia is kind of the big famous one that people know about. But
and just wait, it sank, but it's still at the bottom of, like, it makes up part of the seabed now.
Yeah. Basically the land just got thinner and thinner and thinner until eventually it fell below the level of the seawater and became the seabed. But there's another one in the Indian Ocean, much smaller, called Mauritius. But again, similar process there. Plate tectonic stretched the land.
There must have been like a while just after it happened where you could kind of walk ankle deep. For miles.
A long while. I mean, we're talking about all these geological processes happen incredibly slowly. I mean, the difference between the land being a metre high and the land being exactly level with the seawater surface of the sea, you could have been talking about 1 million years just for that much of a change, know. So we're talking about really, really slow processes here,
Just go for a stroll. You'd you just have the right size shorts. You'd you'd never get wet. Just like for 1,000 kilometers in that direction.
Yeah,
it's just up to your ankles.
Just doesn't come above your knees. Yeah. So that's lost continents. Isn't it funny? All these myths. There's a grain of truth in all these myths. Right. While we're on the subject of myths, let's talk about fairy circles.
Right. Irish fairies. No.
Irish fairies, leprechauns, probably not. I don't know if the leprechauns were fond of being in the sea. Anyway, there are things called seagrass beds. So in shallow enough waters where the sunlight gets down into the seabed, so you're talking about water that's probably 20 meters or 30 meters deep, no deeper than that. You've got these vast areas of seagrass. So it's a plant that's a bit like the grass you have in your garden, looks a bit like it, needs sunlight to grow, and tends to cover large areas in shallow seas. But there are bald patches in these beds of seagrass, and we don't have an explanation for why these bald patches occur.
Age.
Say that again.
Age.
Potentially it's reclining
Every
hair.
bald patch I've ever heard about is age related.
Yeah, or it could be just related to the old Jacuzzi of Despair.
Yes,
people's
stress.
Hair, yeah, stress. People's hair falls out after too much jacuzzi. But yeah, so like there isn't any definite known reason for why these bald patches exist. They're, as I say, they're sometimes called fairy circles. There are some theories. Some people think maybe it's burrowing shellfish that are kind of eating up the roots in certain areas. Others think maybe our friend methane is seeping out of the silt and poisoning the plants in small areas.
A big player. Methane seems to be the big dog down at the bottom of the ocean.
But my favourite explanation is they're alien landing pads for spaceships. Because let's face it, say you're aliens and you want to come and observe the Earthlings, and you don't really want the Earthlings to know you're around. Where else would you land your ship but underwater where nobody will see it? So I reckon these are where the aliens have been landing their ships. And
you have too much free time in your hands.
We just need to set up a camera to watch them, and sooner or later.
So careful travelling like over light years through galaxies to land on Earth and observe us surreptitiously, and they leave a circle in seagrass. How did you discover the aliens?
I can just imagine
the little mistake.
I can just imagine the conversation. Mind the grass, Zorg. Never mind, Blarg, it'll grow back.
There's just one flaw in the strategy.
Right. Let's move rapidly along to glass sponge reefs.
Is there any alien connection to this at all?
Who knows? This could have been how aliens taught us about fibre optics, because it's a really interesting story. So you got the glass sponge reefs, so these really old microscopic glass tubes that are essentially the skeletons of little creatures. So these creatures were able to harvest dissolved silica from the seawater and then form it into tubes around their bodies. Now, I know we were talking about tube worms earlier. They're much bigger creatures. Like a tube worm could be the size of your finger, whereas these things are tiny, tiny little creatures that have microscopic little thin glass. And they lived in huge colonies, so you get this massive network of these little glass tubes where these things used to live. And glass is a very durable substance as long as you don't break it. And, so
that should be a tagline for a glass company.
Yeah,
glass so durable until you break it.
It's great until it's not. So I mean, it was the inspiration for fibre optic technology that we use. Because, so if you imagine normally, if you shine a torch into the night sky, go outside in your garden in the night and you shine a torch, the light dissipates very quickly. So it doesn't travel very far. It might travel, 10, 20 meters away from you, and then suddenly you can't see it anymore. It seems to have like faded away. But the interesting thing about these tiny tubes of glass in the glass sponge reefs is the light beams get reflected over and back inside the tubes, and it allows the light to travel much further distances than it would otherwise. And that is the basic principle of how fibre optic cables work, which we use, of course, for the internet. If you're particularly lucky, you might have fibre optic cables coming into your house for your broadband. But it's like the internal walls of the fibre optic cable allow a beam of light, a laser beam as it happens in the case of computer networks, to bounce over and back inside the reflective walls of the glass tube and travel huge long distances without being degraded.
Now, have you just connected these two things in your own head, or is there actually evidence that somebody went and looked at these things and went...
Yeah, they discovered that these things were transmitting light along their length, much longer than light would normally be transmitted. So yeah, it was part of research into them that gave the inspiration for fibre optic.
Now, obviously, these particular things that aren't at a great depth. I would imagine they couldn't be.
No, I mean, generally most reefs are not that deep.
Yeah.
Most reefs are kind of shallow enough. So that's another weird thing we should talk about is the Milky Sea.
You just collect weird things.
Well, sure, look, how could I otherwise be sitting across the table from you, were it not for my love of weird things?
Weird and the wonderful.
So there was legends from old-time sailors that there was patches of the ocean, like massive patches of the ocean that were glowing a dull, milky, pale kind of colour, only visible at night because it's almost not glowing, but still just about this milkiness you could see in the sea at night time. And for a long time it was just thought to be a sailor's old wives' tale, as it were. But then satellite technology photographed the sea for us from space at night, and sure enough we could see that there are some patches of the ocean that have this dull, milky glow. And it's almost certainly microorganisms like bacteria or plankton or something that are glowing, but we don't actually know what the mechanism is or why it happens, or what's actually happening there.
Drugs, they're on drugs.
It could be a huge bacteria rave.
Yeah. Oh no, I mean the sailors.
Well, I don't think the satellites were on drugs. But but some people might be familiar with the dinoflagellates.
No, nobody is familiar with the dinoflagellates. Dinoflagellates sound like a Tyrannosaurus with a Chalicia belt. Like it's
with a what belt?
That belt, from the Da Vinci Code. Your man flagellates himself.
Oh,
yeah. Is it Chalicia? Maybe it's Chalicia belt or Chalicia.
Well, I'm impressed you remember that, and I'm going to have to accept that you're pronouncing it correctly because I can't remember.
Well,
I remember your man walloping himself all right in the movie, but I don't recall what the thing was called. These dinoflagellates are a different thing. People might be familiar with the idea of certain plankton blooms at beaches at night time. The tops of the waves are sparkling or glowing. That's a different mechanism. There are certain kinds of plankton, fairly common plankton, that when you disturb them, agitate them, splash them around, they for a brief period produce a little sparkle or flash of light. It's kind of a defense mechanism, we think. But that's a different thing altogether.
It's not a very good one. Humans immediately, let's do this. Look at this. Let's look what I can do.
Yeah. I suppose they
didn't realise it was so beautiful.
Yeah, I think it's probably fish and crabs and things that are afraid of the flash of light. But it's cool. I've actually seen it myself once, where there was a really particularly strong bloom of these bacteria, and went down to the beach at night time, and you could literally see the tops of the waves where the waves are breaking were like glowing. Really, it was amazing. And then if you kind of stomped your path up the beach, up the wet beach, and looked behind you, you could literally see this glowing trail of footprints behind you coming up the beach. It was like amazing. I've only seen it once, but it's pretty cool.
Drugs again.
Yeah, could have done with some that night. Water is a weapon.
Water is a weapon.
Water is a weapon, and we're not talking about drowning here. We're talking about
water cannon. Water, people use water cannon.
Yeah. That's true. Actually, I didn't think of
water
that.
bombs in school.
Yeah. Okay, water is more than one kind of weapon. Then I take your point there. Anyway, I'm using that as a segue into talk about a little thing called a pistol shrimp. So it's a cool little name, pistol shrimp, and this little fella, small little crustacean, makes the loudest known sound in nature. And it's a byproduct of what he does to stun his prey. So what he does is he snaps his claws incredibly quickly. So the actual movement of his claws, one of the fastest, it's very short, only a couple of millimeters, but it's one of the fastest accelerations in the natural world. And what happens is that sudden jet of water created by his claw being snapped causes what's known as a cavitation bubble. And that bubble only exists for an instant before it collapses. And when it collapses, it causes a huge noise and a sudden burst of heat in that tiny area where the bubble was, up to 4,000 degrees, which is hotter than the surface of the sun. It's really incredible that this tiny creature can release so much energy just by snapping his claws.
I just don't, there's only, I just have trouble believing this, because why hasn't someone turned this into a superhero?
Yeah,
I don't understand why I haven't seen this Marvel universe.
Yeah,
quick pistol shrimp guy.
Quick. You should patent that idea. You'll make millions when pistol shrimp man.
Pistol shrimp person
bursts onto our movie screens. But yeah, so we should probably talk about what is cavitation. As I said, when the shrimp kind of suddenly clips his claw or snaps his claws, this cavitation thing causes a bubble to appear. So what happens is, if you get a very sudden local surge of water, what will happen is the pressure just around where that surge in the water is will drop for a moment. And if the surge of water has been strong enough, the acceleration of the little squirt of water has been, strong enough, the drop of pressure allows the water to vaporize. And so you get a little bubble made from water vapor. And it only lasts for a second before you get this hot and violent collapse of the bubble again. And it's the collapse of the bubble which actually causes this incredibly loud sound, this little burst of heat and a flash of light. And it's actually both marine engineers have got to be careful about how they design propellers, because boat propellers can inadvertently cause cavitation, and you get when the bubbles, the cavitation water vapor bubbles collapse around the propeller, the shock wave that they cause actually eats little holes into the propeller. So sometimes you look closely at the propeller of a boat, you see all these tiny little holes in it, and it's caused by cavitation.
So cavitation causes the temperature as well.
The collapse
of it.
It's when the cavitation bubble collapses.
Yeah.
It's the sudden compression of that water vapor. So any gas that you compress heats up when you compress it.
Yeah.
But this compresses so quickly, the bubble collapses so quickly that the compression of that little fragment of water vapor is so sudden that it heats up massively.
Very good.
Yeah.
It's
hard to believe, though, that can happen underwater and it can be caused by a tiny little creature.
But I mean, like 4,000 degrees, I mean, that would hurt you if it decided to do it near you.
But the thing is, you're talking about a very tiny area. So you could be talking about a bubble smaller than a pinhead or the size of a pinhead.
Yeah.
So the 4,000 degrees is in a very localized area, and you've got to remember there's cold water all around it. So the heat is going to dissipate very quickly into all that cold water.
But if you were say a Bond villain and you had like 1 million pistol shrimp in a tank, and then there's some guy number 2 that let you down, and you press the button and into the tank of pistol shrimp.
And you could coordinate them all to snap at exactly the same instant. Well, I'm sure you could boil the water, yeah.
There we go. Another idea. I'm going to for free.
The pistol shrimp might boil themselves while they're at it.
Yeah. Well, they probably wouldn't mind.
So, free.
There you go. There's dinner afterwards.
Free meal after you've dispensed.
Actually, that reminds me. Why don't pistol shrimp give money to charity?
I can't wait. I'm on the edge of my seat here. Tell me.
Because they're so shellfish.
Oh,
yes, I've been waiting all day for that one.
I'm sorry, I just can't go on. I'm sorry, folks. We're going to end the podcast here because I just can't.
You can't. Not just this podcast. Every podcast. We're finished now. But
did you know there's gold in that there water?
Okay. Well, yes, you would imagine that there's some soluble bits.
So I'm impressed that you're.
I'm listening. I'm listening to what you're saying. I know I don't look it.
So I don't actually need to explain this. We move on to the next topic. So there is. We were talking about manganese nodules earlier and about how they form from manganese that's dissolved in seawater. But there's other useful metals also. Again, tiny amounts dissolved in seawater. So there's gold, uranium, lithium. All of those things would be useful to us, and there is. Some scientific research going on, but could we extract that stuff out of the water? But you're talking about processing an ocean of water to get a few grams of metal. So, it's a real technical challenge to make it economically viable. And then, of course, like a lot of these things, what are the environmental risks if you do decide to start processing, mind-boggling amounts of water? And how much energy do you have to expend to process that water? I mean, it could be far, far cheaper to mine the stuff out of the earth than to collect it from seawater.
Which we shouldn't be doing anyway.
I mean, I suppose lithium, we all want our batteries in our laptops and phones and electric cars. So lithium is useful for that. So that's probably one reason.
Do you know what they give people who are depressed or to calm them down or something?
Oh, yeah. I think there is a lithium-based medicine.
Yeah. But we should stop using that.
It's also a major component in batteries and rechargeable batteries.
It kind of has the opposite effect on people as it does in batteries.
Yeah, that's interesting.
Pretty much. Yeah.
So the lithium brings down people's energy level, but brings up the battery's energy level. Yeah, it's an interesting dichotomy, that. Right, what else could we get out of the water? Well, the water itself, of course, could give us its constituents, because water is just made from hydrogen and oxygen. It's a compound of hydrogen and oxygen, and hydrogen burns. And hydrogen is a particularly environmentally friendly fuel, because when you burn it, the exhaust is water vapor. There's no smoke, no carbon dioxide, no soot, none of that. If you burn pure hydrogen, the only thing you're going to produce is water vapor. And so, maybe we should be splitting, it's called splitting, when you separate the hydrogen and the oxygen to release those two gases from water. Maybe we should be doing that to generate this environmentally friendly fuel. Problem is, of course, it takes energy to do it. So, there are some experimental attempts with fancy membranes that would allow the hydrogen or the oxygen to pass through and separate that way, which would not involve expending a lot of energy. But I don't think anybody has actually succeeded in getting them to work for more than a few minutes before the membrane gets clogged up with something. So the other classic way of doing it is splitting it with electricity. So if you literally run an electric current through water, the hydrogen and oxygen will bubble off at the point where the electrodes are. But you're talking about using a huge amount of electricity just to get that out. Yeah. So there's probably no net benefit, although some people see it as, instead of calling it producing fuel, it's an energy storage mechanism. So let's say you have a huge amount of solar panels that are generating far more electricity than you need. You could theoretically use the excess electricity to split water and harvest the hydrogen, and at some point in the future use that hydrogen to generate energy or power a fuel, an engine or something.
And how easy is it to store hydrogen? Like, is it particularly volatile?
Yeah, hydrogen is a tricky one to store because the hydrogen molecule is small. So it's able to leak out through the tiniest crack in a metal, or the tiniest imperfection in the welding at the corners of a tank or whatever. So hydrogen tanks typically have to be built very robust. And in fact, just to touch on one of my favorite subjects for a moment, rockets.
The aliens are back.
Rockets, the route to the aliens. So NASA's Artemis rocket is partially fueled by hydrogen, and they've had a huge amount of technical problems trying with leaks, hydrogen leaks, because it is a difficult fuel to contain. So there is that. Yeah. Now Toyota kind of while the whole world was pursuing electric cars, Toyota for a while went off and pursued hydrogen, and they produced a couple of experimental hydrogen cars, thinking that maybe the hydrogen economy, as it's called, might actually become a viable thing. But it doesn't look like the horse that Toyota backed is going to come in.
They haven't figured out how to harvest the hydrogen yet.
Well, I think the availability of high efficiency batteries, rechargeable batteries that we have now, has meant that electric cars are viable, and people have gone down that route instead of the hydrogen route. And they don't have the problems we discussed a moment ago with trying to contain the hydrogen in robust tanks.
Poor Toyota.
Well, Toyota are the richest car company in the world, so I'd say they can cope with it. Yeah.
We're sponsored by Toyota. Our number one sponsors. Toyota for everyone.
Right, let's talk about what the ocean can store for us. Rather than what can we get out of the ocean, what can we put into the ocean?
Nuclear waste.
We've done that, and it's probably not a great idea. There's a very deep canyon between Scotland and Northern Ireland, and there are some nuclear waste dumped in the bottom of that thing, and I don't think anybody thinks it's a good idea now. And there's other places I'm sure that are similar, but no, I'm talking about what useful things can we store in the ocean, and it's carbon really that we're talking about. because as we know, carbon dioxide is the big culprit when it comes to global warming and climate change and all that. Carbon dioxide that's in the air dissolves into seawater. So the air obviously is in contact with the surface of the sea, and a certain amount of carbon dioxide that's from the air dissolves into the seawater and forms a solution of what's called carbonic acid. So that gets stored in, that's a certain amount of carbon dioxide that gets stored in the sea. But then there's also a different mechanism called marine snow. So, the bodies of animals and plants are substantially built from carbon. And when those animals or plants die or start to decompose, if they're in the sea, fragments of them start drifting down towards the seabed. And, so you're talking about partially decomposed animal and plant remains. You're also talking about fish poo.
Great.
All
You're
that
having
stuff,
your dinner.
all that stuff kind of, gradually sinks down towards the seabed, and it's known as marine snow. And it tends to build up on the seabed and get stuck in the sediment. Now, as we mentioned earlier, methane, it slowly decomposes into methane, and some of that methane does get released back into the atmosphere. Methane is actually a worse greenhouse gas than carbon dioxide. So,
and sinks ships.
So and theoretically sinks theoretical ships in theoretical Bermuda triangles. It's a double-edged sword, that one. And the other problem with, obviously there's more carbon dioxide in the atmosphere now, and the combination of the fact that there's more of it in the air and the fact that seawater is getting warmer means that more of it is dissolving into the sea. And that, although it might sound like it's a good thing, is actually making the seawater more acidic. And there are some of the creatures that live in the sea, they have evolved to live in a less acidic environment. So that more acidic ocean now is starting to have bad effects on them. So
is that the one about the corals? The corals are being bleached. Is that sort of a...
Is that... Yeah, I think that's one component. And then some shellfish, the calcium shells that they build for themselves are not resistant to acidic water, and the shells are getting thinner and less substantial. So there are downsides to more carbon dioxide dissolving into the sea. Now, I think probably the coolest story today that I think, leaving aside...
There's been a lot of cool stories.
Leaving aside the pistol shrimp and his
pistol shrimp was good, and the zombie bacteria was good.
Yeah, and of course the Jacuzzi of Despair.
And Jacuzzi of Despair is just the best name.
Anyway, this one is the secret whale chat line.
Wow, I can't see that taking off.
So it's a natural phenomenon called the SOFAR channel, sometimes referred to as the superhighway of sound. So between the depth of about 600 and 1200 meters below the surface of the sea, the way that pressure and temperature interacts causes a kind of an invisible boundary, and sound is able to bounce off that, get reflected off that. So this is a very similar phenomenon to the glass sponges we were talking about earlier, in that, fiber optic, we mentioned they're related to fiber optic cables, and inside fiber optic cables, the light bounces off the inside of the surface of the cable to get reflected down along the length of the cable. Well, this SOFAR channel is similar for sound. So you get these two boundaries, an upper boundary or a shallower boundary and a deeper boundary, that these things are invisible, but they're formed by the pressure and temperature of the water, and low frequency sound waves can literally bounce off them. And you literally get, it's like a channel, a tube that goes through the ocean and allows these sound waves to travel much further than they otherwise would. And it's quite likely that whales who produce low frequency sounds make use of them to keep in touch with each other over very long distances.
So we should broadcast the podcast in that channel.
If we could find somebody who could translate it into whale for us, that would be excellent. Yeah.
Drop a sea drone down there, just like with a speaker.
Yeah. And I wonder, would the humour transfer over?
You never know. We could become leader of the whales.
I strongly suspect the humour doesn't even transfer to a lot of humans.
Well, most humans won't get it.
Anyway, it's called the SOFAR channel, and of course humans have found a use for it. The military have figured out how to use it to listen for the presence of enemy submarines far away, and scientists can use it to listen for far off undersea earthquakes and landslides and things like that, things that make large low frequency sounds. So yeah, it's
so basically they have like listening devices in there, down there for
at those depths.
Those depths.
Yeah. So it's pretty amazing. Now, we mentioned lithium earlier on and batteries. Some people think the sea itself might be a battery because salty water allows electricity to flow because of the salt ions in the water. And if you get a place where salt water and fresh water are side by side, the difference in the salt concentration allows a current to flow across the boundary from salt to fresh. And some people think you could maybe harvest that electricity out of the sea and treat the sea like a great big battery. But of course, you're talking about minute amounts of electricity. So you would have to have a very large harvester over a very wide area, say at the mouth of a big river where fresh water from the river is meeting the seawater. Is it viable? Who knows? But some people are thinking about it anyway.
Good. Well, all of these things could come to fruition.
Right. And today we're going to finish up with the wonderful subject of jelly. Jelly here, jelly there, jelly everywhere. So the fact is, we are slowly turning the ocean into a paradise for jellyfish. What we're doing to the ocean, they love.
They like the additional carbon, do they?
Well, I don't know about the carbon, but they certainly like the fact that the sea is warmer. So the warmer seas tend to have lower oxygen concentration in them, and that tends to suit jellyfish more than other creatures. A lot of their predators, we have fished them out. So, we have certain species that eat jellyfish. We have fished out those species and their numbers are far lower, so that there's much less predation of jellyfish going on. And then our farmers understandably like to use fertilizer to maximize their crop yield. That fertilizer gets washed into rivers and eventually finds its way into the sea. And the plankton, which are minuscule plants that a lot of jellyfish species eat, love that fertilizer because they're plants. Why wouldn't they love it? So you get these big plankton blooms being encouraged by fertilizer, and that also encourages blooms of jellyfish. So there are massive blooms of jellyfish happening now that didn't happen before. And even here in Ireland, we had it on the south coast for a few days last year. We had what they call mauve stingers. We had millions of them. And luckily they didn't stay around very long. But another side effect of these greater numbers of jellyfish is that they sting juvenile fish. Some of them do. Some species sting small little juvenile fish. And so you could get an entire generation of juvenile fish being wiped out by a big bloom of jellyfish. So it's funny as it might sound, it's not funny at all.
Yeah, it's not just about getting a jellyfish sting while you're on holidays. It's slightly more.
Yeah, and they could be just everywhere, and they could reduce the diversity of other species in the sea because they're going to outcompete them.
Yeah, just like kind of fire ice cream at them.
Yeah, or the methane fire ice. We could
fire ice. We could, yeah.
So that's kind of all we have today, Joe.
I think that was quite a lot. I think you very lucky listeners to this podcast today. There was a lot of information there.
Yeah. So I don't know. Have we any parting shots to leave with our listeners?
I decided zombie bacteria was like prime for a limerick.
Right.
So we'll leave you with this poetic license in its. So to qualify as zombie bacteria, you must satisfy some strict criteria. You metabolize slow, keep the temperature low, and avoid causing human hysteria. There you go.
I'll tell you,
a week.
You're wasted on this podcast.
No, but I will be in about 5 minutes. Thanks for listening this week.
Yes, that is enough with the science, and that is more than enough science this week, I think. And thanks for listening, and don't forget your homework, and we'll see you next week. It's goodbye from me, Senan.
Okay, it's goodbye from Joe. Take it easy.